Dear students, today we will discuss an important topic, moving charge magnetism. This is actually 12th second year topic. So the mains point of view, the weightage of this chapter is one or two questions from mains, definitely two questions from NEET. So this is one important topic. So moving charge magnetism. Now, when a charged particle is at rest position, charge is at rest. Consider a charge Q which is at rest position. If it is at rest position, it induces only electric field around it. There is no magnetic field induced around these charged particles. Okay, so now it induces only electric field, which means electric field E equals to not equals to 0, E not equals to 0, and B equals to 0. Now, rest charge induces only electric field around it. Now, there is no magnetic field induced around the rest charge. Okay, now the characteristics of this rest charge is called electrostatics. Now, anyway, here you can write one point: rest charge induces only electric field around it. Only electric field around it. Okay, the what is the induced magnetic field induced by rest charge? That is 0. Suppose the same charge is moving with some velocity v. This charge is moving with some velocity v. Now, it induces both electric and magnetic field around it. The moving charge induces both electric and magnetic fields around it. E not equals to 0, which means electric field is induced, and B is also not equals to 0, which means magnetic field is also induced. But here, rest charge induces only electric field. Now, the characteristics of this rest charge is called electrostatics. But moving charge induces both electric and magnetic field around it. Now, we can write one point here: moving charge induces both electric and magnetic fields, around it. Okay. Now, already this electric field we have discussed in electrostatics. Now, we are going to discuss magnetic field around this moving charge. Now, what is the chapter name here? Moving charge magnetism. Due to the moving charge, here charge is moving with some velocity. Due to this charge, moving charge, magnetic field is induced. That's why. So this is called moving charge magnetism. So anyway, what is the best example for moving charge? Best example for moving charge. That is electric current. Best example for moving charge, electric current. Now, the rate of flow of charge carrier, that is called current. When the charge is moving in some velocity or moving, or flow of this charge is called current I. Okay? So we can write one conclusion. Moving charge means, so this is current carrying conductor. This is considered as one current carrying conductor. This moving charge induces magnetic field around it. This moving charge induces magnetic field around it, which means the flow of charge is considered as a current. This is considered one current carrying conductor. It is also induces magnetic field around it. So every current element induces a magnetic field around it. Now, consider one current carrying conductor carrying a current I. So consider one current carrying conductor carrying a current. Now, every current element induces some magnetic field around it. It induces magnetic fields around it. So this magnetic field induces around the current carrying conductor. There is no induced magnetic field on the axis of conductor or along the axial line of this conductor. Magnetic field is induced around this conductor. There is no magnetic field along the length of conductor or on the axis of conductor. Right? Suppose consider this is one current carrying conductor. If current is passing through the conductor is I, now then magnetic field is induced around this conductor. So the magnetic field is induced only around this conductor. There is no magnetic field along the length of conductor. Okay? If you consider one straight line along the length of this conductor, this is axial line or axis of the conductor, there is no magnetic field induced around this conductor. around the axis of this conductor. This magnetic field is induced around this conductor. So anyway, every any current element induces a magnetic field around it. Now, this magnetic field, we have to measure this magnetic field. Anyway, this magnetic field is vector or scalar. So any vector, any magnetic field, that should be a vector. So we have to measure this magnetic field, induced magnetic field. This induced magnetic field is a vector. Is a vector. Every vector has both direction and magnetic field, magnitude. So vector has direction and magnitude. So induced magnetic field is a vector. It has both direction and magnitude. So we have to measure the direction of induced magnetic field and we have to measure the magnitude of induced magnetic field. So how can we measure the direction of induced magnetic field? So by using right-hand thumb rule, by using this right-hand thumb rule, we can measure the direction of induced magnetic field by using Biot-Savart's law and Ampere's law. Biot-Savart's law and Ampere's law. By using this Biot-Savart's law and Ampere's law, we can measure the magnitude of induced magnetic field. Okay. So finally, we can write on magnetism. Current carrying conductor induces magnetic field. That induced magnetic field is a vector. So every vector has both magnitude and direction. We have to measure the direction of induced magnetic field by we have to measure the magnitude of induced magnetic field. How can we measure the direction of induced magnetic field? Means by using right-hand thumb rule, we can measure the direction of induced magnetic field. By using Biot-Savart's law, we can measure the magnitude of induced magnetic field. Right-hand thumb rule. Now, what is the use of this right-hand thumb rule? It is used to find the direction of induced magnetic field. It is used to find the direction of induced magnetic field. Induced magnetic field. Okay. Now consider in this right-hand thumb rule. Consider this right hand. Okay. Now this thumb is always stretched. Okay, along a straight line. Now stretch like this. These fingers are bent like this. Okay. In right-hand thumb rule, so right hand we have to stretch like this. Thumb is along a straight line and fingers bent like this. Okay. So in this case, first case, if current carrying conductor is a straight line, but linear currents, which means linear currents means current carrying conductor is a straight line. It may be circular path or along a straight line. In case of straight line, if it is along a straight line, so how can we measure the direction of induced magnetic field? Okay, before going to this one, if the magnetic field is inside, magnetic field is inside. Inside means inside the board, so that is indicated by into. Okay, if magnetic field is outside, that is indicated by the. If you want to consider, one is considered positive, other one should be negative. Okay, the magnetic field is inside the board, that is considered positive. If the magnetic field is outside the board, that is considered negative. Now, first case, currents are linear currents. Now, in this linear current, we consider one current carrying conductor carrying a current I. Okay, now any current carrying conductor induces magnetic field around it. So, it induces magnetic field around it. Now, what is the direction of magnetic field in this plane and in this plane? Now, by using this right-hand thumb rule, we can measure the direction of magnetic field. So, arrange this term. Okay, in right-hand thumb rule, so what is the current wire is along the straight line. Now, so here thumb is along the straight line. Arrange this thumb along the direction of current. Then 12 fingers gives the direction of magnetic field. So, when the current is linear current, arrange this thumb arrange along the direction of direction of current. Then curled fingers. Curled fingers means, so this middle finger, curled fingers gives the direction of magnetic field. Magnetic field. Curled fingers gives the direction of magnetic field. Now, this is one current carrying conductor carrying a current I. Now, so due to this current carrying conductor, magnetic field is induced around this. Now, what is the direction of induced magnetic field in this plane and in this plane? So now, arrange this term along the direction of current. Then curled fingers gives the direction of magnetic field. So in this plane, arrange this term along the direction of current. Now, curled fingers. Curled fingers are inside the hole in this plane. Now, what is the direction of magnetic field in this plane? What is the direction of magnetic field? Inside. Because the curled fingers are inside. Okay. So if thumb is arranged along the direction of current, curled fingers are inside the hole, which means the magnetic field is inside. So what is the direction of magnetic field in this plane? So again, arrange this thumb along the direction of current. Then curled fingers in this plane, the curled fingers are out of the board, outside, like this, outside. So like this. Okay. What is the direction of magnetic field in this plane? That is outside. Outside means, so we have to write, indicate with the dot. Inside means input. Now, what is the direction of magnetic field in this plane? Outside. So this is inside. What is the direction of magnetic field here? Outside. Outside. Okay. So now direction of current. So this let's say again. Now current is come along the direction of current. Curled fingers are inside. The magnetic field, direction of magnetic field in this plane is inside. Now, so in this plane, arrange this come along the direction of current. Curled fingers are outside. Curled fingers are outside means magnetic field is outside. Suppose the current is moving downward direction like this. Now this is one current carrying conductor carrying a current I. So due to the current carrying conductor, magnetic field is induces around it. Okay, magnetic field is induces around it. What is the direction of magnetic field in this plane and in this plane? So for linear currents, arrange this term along the direction of current. So thumb arrange along the direction of current. Current is downward direction here. Arrange this thumb along the direction of current, so downward direction. What is the direction of magnetic field in this plane? Curled fingers are outside. Curled fingers are outside means direction of magnetic field is outside. Outside, that is indicated by dot. So which means magnetic field is outside. Now what is the direction of magnetic field in this plane? Okay, arrange this term along the direction of current. Curled fingers are inside the board. Now the direction of magnetic field is inside. Okay, in this one, in this plane, curled fingers are outside. In this plane, curled fingers are inside. So here magnetic field is out of the board. Now here magnetic field is inside. The direction of magnetic field in this plane is inside. Into means inside. Okay, so if the current is upward direction, so what is the direction of magnetic field in this plane? Inside. In this plane, outside. Current is downward direction. Okay, what is the direction of magnetic field in this plane? Outside. Curled fingers are outside means magnetic field is outside. So what is the direction of magnetic field in this plane? Inside. Okay. So this is in case of linear currents. So current may be current conductor, may be linear or circular. Okay. So in the second case, we will discuss about circular currents. Case 2, circular currents. Circular currents means current carrying conductor is in circular path. So in this case, we have to measure the induced magnetic field. What is the direction of induced magnetic field? So in circular currents, okay, so to find the direction of magnetic field, we are using right hand thumb rule. In this right hand thumb rule, we have to stretch this thumb along this direction, along the straight line. So fingers should be bent like this. Okay. So here in case of circular currents means current carrying conductor. Current is in circular path. So here circular path is curved fingers. These curved fingers we have to arrange along the direction of current. Then thumb is the direction of magnetic field. Here circular path is, what is the circle? Now in circular path, current is in circular path. Now here in circular path is curved fingers. These curved fingers we have to arrange in the direction of current. Then thumb is the direction of magnetic field. In case of circular currents, now curved fingers. Arrange these curved fingers. Arrange along the direction of current. Then thumb gives the direction of Direction of magnetic field. Direction of magnetic field. Thumb gives the direction of magnetic field. So, for example, consider one current carrying conductor. It is in circular path. This is the circular wire carrying a current I. Okay, this is one circular conductor carrying a current I. Now, due to this one, magnetic field is induced. Okay, what is the direction of magnetic field? Okay, so in case of circular currents, now curl fingers. We have to arrange these curl fingers around the direction of current. Okay, in thumb right and thumb rule, so curl a circular path. These curl fingers are along the circular path. Here the circular path is current direction. Current is in the circular path. Now here circular path is curl fingers. But we have to arrange these curl fingers along the direction of current. That thumb is the direction of magnetic field. So now this is current. Now curl fingers, arrange these curl fingers along the direction of current. Now what is the direction of thumb here? Thumb is inside the board. Thumb is inside. So arrange these curl fingers along the direction of current. So now see here, thumb is inside the board. Now which means direction of magnetic field is inside. So in this case, magnetic field is induced. What is the direction of magnetic field inside? Inside means that is represented by into. Okay. Suppose the current is in anti-clockwise like this. Now this is one circular current carrying conductor carrying a current I. Okay, in anti-clockwise direction. Okay, along this direction. Due to this, again magnetic field is induced because it is a current carrying conductor. What is the direction of induced magnetic field due to this current carrying conductor? Now, so in current is in circular path. Now in right hand thumb rule, what is the circular path? Okay, circular path. Curved fingers are in circular path. Okay, so arrange these curved fingers along the direction of current. Then thumb is the direction of magnetic field. Okay, so by arranging these curved fingers along the direction of current, now thumb is out of the board. Now due to this, magnetic field is induced outside of the board. Out of the board. Okay, outside means that is represented by dot. Now magnetic field is here outside. Okay, arrange these curved fingers along the direction of current. Then thumb gives the direction of magnetic field. Here, thumb is out of the board. The direction of magnetic field is out of the board. So in this case, current is in clockwise direction. Curved fingers, arrange these curved fingers along the direction of current. Then thumb is the direction of magnetic field. So that is inside the board. So thumb is inside the board means induced magnetic field is inside the board. Okay, so by using this right hand thumb rule, we can measure the direction of induced magnetic field. Okay, so induced magnetic field is a vector. This vector has both magnitude and direction. Already we have measured what is the direction of induced magnetic field. Okay, by using this right hand thumb rule. So again, we have to measure the magnitude of induced magnetic field to find the direction of magnetic field. Magnitude of induced magnetic field, we are using Biot-Savart's law. What is the use of this Biot-Savart's law? It is used to find the magnitude of induced magnetic field. Induced magnetic field. It is used to find the magnitude of induced magnetic field. Okay. Now consider one current carrying conductor. This current carrying conductor may be straight line and circular path, okay, any shape. So any shape of the conductor. Consider one conductor in any shape, not only straight line and circular path. Now consider one conductor carrying a current I. Okay. Due to this current carrying conductor, magnetic field is again induced. Okay. So magnetic field is induced around this conductor. Because it is a one current carrying conductor. Now we have to measure the direction of magnitude of induced magnetic field due to this current carrying conductor. Now consider one point. Here we have to measure the magnetic field due to this current carrying conductor. Now, which is at a distance r from the current carrying conductor. Due to this current carrying conductor at a distance r, what is the magnetic field? That is V. We have to measure this magnetic field. So this current point means current carrying conductor, it may be kilometers or miles, okay, very long. So due to that reason, we have to consider an elemental length, a small part. Okay, now consider a small part of the wire, current carrying conductor. The length of of this part is considered dl. Now the same amount of current is passing through this conductor. Okay, so same current I is passing through this conductor. Due to this current element, what is the magnetic field? We have to measure the magnetic field. Okay, at a distance r. Now, due to small wire, the magnetic field is also small, that is dB. Due to the total conductor, the magnetic field is B. Due to the small wire, small part, the magnetic field is also very small, that is indicated by dB. Okay. Now, we have to measure the magnetic field at a distance r from the current element, that is assume B. Now, this elemental length makes an angle theta with position vector, distance vector. Now, the induced magnetic field at this point, that is dB is directly proportional to the induced magnetic field dB at a distance r from the current element, that is dB is directly proportional to the current passing through the conductor, which means current passing through the conductor increases, the magnetic field at this point also increases. What is the relation between these two? If current increases, the magnetic field is also increases. So that's why you can write the magnetic field at this point dB is directly proportional to light. Now dB is directly proportional to length of this conductor, Now when length is also increases, the magnetic field is also increases. Now the magnetic field dB is directly proportional to sine angle, and magnetic field is dB is directly proportional to or inversely proportional to the square of distance. If the distance increases, the magnetic field is decreases. What is the relation between distance and magnetic field? That is dB is inversely proportional to the square of distance. From this all rays we can find on conclusion, the magnetic field at this point dB is directly proportional to I dl sin theta by r square. Magnetic field at that point that is equals to dB is directly proportional to I dl sin theta by r square. Okay, by removing proportionality symbol. If you want to remove this proportionality symbol, we have to write one constant. In case of electricity, what is the constant? Electricity or electrostatic. Okay, electric field. What is the proportionality constant? That is 1 by 4 pi epsilon naught. In case of magnetic fields, what is the proportionality constant? That is mu naught by 4 pi. So here we are discussing about magnetic field. After removing this proportionality symbol, we have to introduce one constant. That constant is mu naught by 4 pi. Now we can write the magnetic field dB equals to, after removing proportionality symbol, write down one constant mu naught by 4 pi into I dl sin theta by r square. That is a magnetic field due to the small elemental length dl. Okay, at this point. Now, due to the entire conductor, what is the magnetic field at this point? Due to the total conductor means how can we get the total length? By integrating. So by integrating, we will get the total length. Okay, we will get the total magnetic field due to the entire conductor. So integrate both sides, integral dV that is equal to mu naught by 4 pi integral I dl sin theta by r square. Right? Integral dV makes the values be mu naught by 4 pi. Okay, I we can write outside also. Okay, mu naught by 4 pi dl sin theta by r square. So what is the magnetic field at a distance r from the current carrying conductor? That is B equals to, what is the magnetic field? Mu naught I by 4 pi into I dl sin theta by r square. Okay. So now write down in exam point of view, sometimes I will give in another format in vector notation. Okay. So now integrating here B is equals to, you can write like this. Now, what is the magnetic field of mu naught by 4 pi? I dl mu naught by 4 pi dl sin theta by r square. Right? First, in another form, vector form. Let us see in vector form. Now, suppose A cross B. How can we write the A cross B value? Suppose two vectors A and B are two vectors. A cross B, we can write AB sin theta. The magnitude of A cross B, we can write AB sin theta. The magnitude of A into magnitude of B into sin theta. Okay. Now here, suppose DL cross R cap. DL cross R cap, we can write DL magnitude of R cap sin theta. Right? So if your R cap is a unit vector, what is the magnitude of R cap? That will become 1. Because R cap means it is a unit vector. Now the magnitude of unit vector will become 1. Now this will become dl sin theta. that is equals to dl cross r cap, right? So in this place, in dl sin theta, okay, instead of this dl sin theta, we can write dl cross r cap. Now we will get in another format. The same formula we will get in another form, vector form. So mu naught by 4 pi into, instead of dl sin theta, we can write dl cross r cap by r square. Okay, so in another form we can write like this: r cap, how can we write the unit vector r cap, that is equals to vector r by magnitude of r. Simply we can write vector r by r. Now substitute this r cap value in this equation, then we will get mu naught by 4 pi dl cross r cap value. What is r cap value? R vector r by r into r cube. This is another form. Okay, so here dl cross r cap, if it is r cap, the denominator should be r square. If it is r vector r, that should be r cube. If you want to measure only the magnitude, that b equals to mu naught by 4 pi into dl sin theta by r square. That is the only magnitude. In vector notation, if it is r cap, you can provide here denominator r square. If it is r vector r bar, then denominator should be r cube. Okay, this is the previous question. Now let us see applications of Biot-Savart's law. Applications of Biot-Savart's law. Applications of Biot-Savart's law. Right. Already we have derived. Now what is the magnitude of magnetic field for the current carrying conductor, that is mu naught by 4 pi into dl sin theta by r square. Okay, by simplifying this equation, we will get one formula. Okay, now current carrying conductor. Consider one current carrying conductor carrying a current I. This is one current carrying conductor carrying a current I. Right. Now we want to measure the magnetic field at a distance on the current carrying conductor. At a distance on, what is the magnetic field at this point? That we have to measure, right? Now, one end of the conductor, this is one end of the conductor, this is the other end of the conductor carrying a current I. What is the magnetic field at a distance r from the conductor means? Now, this end of the conductor makes an angle alpha at the measuring point. We are measuring the magnetic field at this point. Now, at this end, okay, at this point, one end of the conductor makes an angle alpha. Another end of the conductor makes an angle beta at the measuring point. Okay, in terms of alpha and beta, what is the magnetic field at this point? That is V equals to, remember this formula. So this is actually derived from previous formula. Okay, proven by credential, right? mu naught I by 4 by r into sin alpha plus sin beta. What is the magnetic field at a distance r from the current carrying conductor? Okay, in terms of alpha and beta, mu naught I by 4 pi into sin alpha plus sin beta. Here alpha, beta are the angles, okay, at the measuring point. One end of the conductor makes an angle at the measuring point, that is alpha. Another end of the conductor makes a beta at the measuring point. Okay, so at the end of the conductor, suppose that at the end of the conductors consider the angles theta 1 and theta. So here alpha and beta are angles at the measuring point. Theta 1, theta 2 are angles at the end of the conductor. Okay, so consider this is one right angle triangle. Just like a right angle triangle. Now sum of angles in a triangle is 180 degrees. Now in another point, this is the first formula. Okay, what is the magnetic field at a distance of mu naught I by 4 pi into sin alpha plus sin beta. Now, in terms of theta 1 and theta 2, what is the formula? Same formula we can write like this. Now, consider this is one right angle triangle. Sum of angles in a triangle is 180 degrees. So, this is right angle triangle means already is 90 degrees. Now, the sum of remaining should be equals to 90 degrees. Now, on theta 1 plus alpha should be equals to 90 degrees. Okay, so now from this equation we can write alpha equals to 90 minus theta 1. So similarly, this is another right angle triangle. Right angle triangle means one angle is 90 degrees. Now sum of angles in a right angle, sum of angles in a triangle is 180. So right angle means already this is 90 degrees. The sum of two angles, remaining two angles should be equals to 90 degrees. So it means beta plus theta 2 or theta 2 plus beta, that should be equals to again 90 degrees. That should be 90 degrees. Now from this we can find beta equals to 90 minus theta 2. Now alpha and beta values substitute in this equation. Now then we will get the magnetic field due to current carrying conductors in terms of theta 1 and theta 2. Now what is the formula? Magnetic field formula mu naught I by 4 pi r into sin alpha plus sin beta. Sin alpha plus sin beta. So B equals to mu naught I by 4 pi r sin alpha value. What is the sin alpha? Alpha value is sin 90 minus theta. Beta value means sin 90 minus, this is a theta. Sin 90 minus theta. Now sin 90 minus theta value sin theta. Now what is the magnetic field? Mu naught I by 4 pi r sin 90 minus theta 1, sin theta 1. Plus this cos theta. Sin 90 minus theta will cos theta. This value will become cos theta 1 plus cos theta 2. Cos theta 1 plus cos theta 2. Right. This is the magnetic field formula due to the current carrying conductor. So this is in terms of alpha and beta. So what are the alpha and beta? These are the angles at the measuring point. Angles at the measuring point. So this is in terms of theta 1 and theta 2. Now what are the angles theta 1 and theta 2? Theta 1 and theta 2 are the angles at the end of point. Angles at the end of point consider theta 1 and theta 2. Angles at the measuring point consider alpha and beta. So this is a magnetic field in terms of alpha and beta. So suppose this conductor, current carrying conductor is infinite length. So infinite means very long. Infinite conductor. Infinite conductor. Current carrying conductor. So infinite means not very long. Infinite into infinite numbers no student physics law. Very long is considered infinite. Now consider one conductor like this, carrying a current I. Length of this conductor is very long. This side is extended to infinite. This side is also extended to infinite, means very long. So this is one conductor, current carrying conductor, consider conductor. So this side and this side and this side extended to very long length. That is considered infinite conductor. Right? Now due to this infinite current carrying conductor, we have to measure the magnetic field at a distance of. Now at a distance of, what is a huge magnetic field? Magnetic field B value. Right? Now what are the alpha and beta values in this case? In case of infinite conductor, what are the alpha and beta values? Now alpha means this is the angle made by the one end of the wire at the measuring point. This is alpha. If length of conductor increases, then alpha values increases like this. Similarly here, so alpha means one end of the conductor makes an angle at the measuring point. If length of conductor increases, alpha value increases, so it will become maximum value will become 90 degrees. So what is the angle between these two? 90 degrees, right? Now in case of infinite point, alpha value will become 90 degrees and beta values also will become 90 degrees. So if you want to measure theta 1 and theta 2, theta 1 will become 0 and theta 2 will become 0. If it is 90 degrees, there should be 0. So what is the reason? Already 90 over 80. Sum of angles made, triangle is 180 degrees. That's why if you look at theta 1 and theta 2 should be 0. Alpha and beta both are will become 90 degrees. Now alpha and beta values substitute in this equation, that we will get the magnetic field at a distance of the current carrying conductor. So what is the magnetic field formula? Mu naught I by 4 pi r sin alpha plus sin beta. We can use either of these two formulas in terms of theta 1 and theta 2 and alpha and beta. So anyway, alpha and beta values are 90. Now substitute in this equation, B equals to mu naught I by 4 pi r sin alpha sin 90 plus sin 90. So sin 90 value is 1 plus 1 2. Now we get what is the magnetic field? 4 mu naught I by 4 pi r into 2. 2 1 times 2 times. So B equals to mu naught I by 2 pi r. That is a magnetic field due to the infinite conductor, infinite current carrying conductor. So we have to remember this formula directly. So we need not solve in every time. So in case of infinite wire, what is the magnetic field? Mu naught I by 2 pi r. Infinite or that is also called as very long. Very long is nothing but infinite conductor. So that is a magnetic field. Let us see another application. Fourth application, semi-infinite conductor. Semi-infinite current carrying conductor or wire. Semi-infinite means one end is extended to infinite, another end is fixed. Suppose wire, consider one wire. So it starts at this point, this is a fixed end, other end of the conductor is extended to infinite. So that is considered semi-infinite wire. Right. Now consider one semi-infinite current carrying conductor like this. Carrying a current I. Now this is a fixed end, and other end is extended to infinite. Now we want to measure the magnetic field at a distance r from this current carrying conductor. What is the induced magnetic field at a distance r? Like this. So which is at a distance r. In this case, this length is extended to infinite means what is the angle? How an angle alpha will become 90 degrees. There is no length this side. That side beta. There is no beta value. Beta is 0. Now substitute this alpha and beta values in equation. mu naught by 4 pi r sin alpha plus sin beta. Right, magnetic field B equals to mu naught by 4 pi r sin alpha value is sin 90 plus sin beta value is sin 0. Sin 0 value is 0, sin 90 is 1. Finally, you get what is the magnetic field to this semi-infinite wire mu naught by 4 pi r. Okay, remember this formula. So, what is the induced magnetic field due to the semi-infinite wire, that is mu naught by 4 pi r. So, due to the infinite conductor, the value is mu naught by 2 pi r. So, we have to remember these two formulas. Okay, sometimes they will give finite length, not infinite, semi-infinite. They will give some length, some finite length. Another application, let us see finite length. The length of conductor is limited, some finite value, right? Now this consider current carrying conductor, carrying a current I. The total length of conductor is considered 2a. What is the length of this conductor? 2a. Now consider this is a midpoint. Okay, from midpoint to one end of the conductor, that length is here. From midpoint to other end of the conductor, that is length here. We have to measure the magnetic field at distance r from the current carrying conductor. Here we have to measure the magnetic field, right? So now, one end of the conductor, this is one end of the conductor makes an angle alpha at the measuring point. Another end of the conductor makes an angle beta at the measuring point. Alpha and beta values. Now this value is r, this value is here. Now this will become, this is one right angle triangle. Now this will become hypotenuse. What is the value? This distance will become so L square plus r square. Now this is r and this is L, and anyway this is a right angle triangle. So this length will become hypotenuse of this right angle triangle. This length is L square plus r square. Okay. Now what is the sin alpha value and sin beta value from this diagram? Sin alpha. Okay, sin beta both are will get the same values. Sin means opposite by hypotenuse. For this alpha, opposite is here, hypotenuse is under root of L square plus r square. If you want to measure sin beta value, what is opposite? Opposite value is here, hypotenuse is under root of L square plus r square. Now sin alpha, sin beta both are will become L by under root of opposite L by under root of L square plus r square. Now substitute this value, these values in the equation. What is the magnetic field at a distance r from mu naught by 4 pi r? Then value sin alpha plus sin beta. Right? B equals to mu naught by 4 pi r. What is the sin alpha value? Sin alpha, sin beta both are equal. So we can write 2 times of L by under root of L square plus r square. So 2 1 times 2 2 times. Okay, B equals to mu naught I by 2 pi r into L by under root of L square plus r square. L by under root of L square plus r square. This is magnetic field with the finite value. If random finite value is there, so otherwise, if it is infinite value means we will have to remember directly formula, that is mu naught I by 2 pi r. Okay, if it is semi-infinite wire I learned for you. So formula directly the formula with this one. If you remember these formulas, we can find we can solve the problems easily. Okay, problems are related easy. Okay, and we can direct the formula with this one. Right. So in case of linear currents, current conductor this linear straight wire. Some of the current carrying conductor is in circular path. So what is the induced magnetic field to the circular currents? Let us see another application. In the last case, we have discussed the applications of linear currents. Okay, linear currents applications. If current is in circular path, so what are the applications? How can we measure the direction of magnitude of induced magnetic field? Okay, in this case, circular currents. So first consider arc. Arc means a part of circle. Okay. A circular arc like this carrying a current I. The current passing through this arc is R I. Now the radius of this arc is R. Radius is R. What is R? It makes an angle theta at the center. What is the magnetic field at the center of this arc? Okay. Consider R. R means a part of circle. Now what is the carrying a current I? What is the induced magnetic field at the center? So induced magnetic field. We have one formula, directly one formula. So magnetic field at the center of arc is magnetic field. Magnetic field means field direction. Magnetic field at the center of arc. Center of arc is that formula V equals to mu naught I by 4 by R theta. Theta means what is the angle made by the arc. That is the magnetic field to the arc. Suppose it is a circular coil, current coil. Second one, consider another application, current coil. Okay, so what is the theta? Coil means circular, circle. One circle, complete circle. What is the theta value for complete circle? Theta will become 2 pi, 2 pi radius. Here, we have to consider theta in terms of radians. Theta is considered in radians. Not in degrees, consider in radians, then only you will get the magnetic field at the center. Now, for current coil or complete ring, so theta will become 2 pi radius. Now, this is one current coil carrying a current I. The radius of this current coil is R. Now, what is the magnetic field at the center of this coil? Now, the magnetic field at the center of the coil is magnetic field at the center of the coil. Center of the coil is okay. V equals to mu naught I by 4 pi R into theta. What is the theta value? Theta for current coil that is 2 pi radians. Now, so this will here we look at mu naught I by 4 pi R into 2 pi. Now here pi cancel to 1 times 2 2 times. Finally, we will get the magnetic field to the center of current coil that is mu naught I by 2 R. Remember this formula. What is the magnetic field at the center of current coil that is mu naught I by 2 R? Suppose N turns. Here coil has only one turn. Okay, 50,000 turns. So in case of N turns, what is the magnetic field? For N turns, the magnetic field at the center of coil is V equals to N into mu naught I by 2R. For single coil, single turn, only one turn, what is the magnetic field at the center? V equals to mu naught I by 2R. If it has N turns, for N turns like this, N turns, number of turns is N, carrying a current I, radius is R. What is the magnetic field at the center? So magnetic field to the center of the coil to the N turns, N into mu naught I by 2R. Okay. So next one is third application, semicircular coil. Semicircular coil. Semicircular coil. For semicircular coil, theta value will become pi radius. Now consider one current carrying conductor. Okay, semicircular coil. The radius of this coil is R. Now, what is the magnetic field at the center? What is the induced magnetic field at the center of the semicircular coil? So, what is the formula for R? Mu naught I by 4 pi R into theta. What is the theta value here? Pi. So, then we will get the mu naught I by 4 pi R into theta value pi radius. Pi cancel. Due to the semicircular coil, mu naught magnetic field at the center is mu naught I by 4R. Now, due to the circular coil, what is the magnetic field at the center? Mu naught I by 2R. Due to the semicircular coil, what is the magnetic field at the center? Mu naught I by 4R. Suppose 1 by 4th circle, quarter circle, 1 by 4th circle, what is the magnetic field? 1 by 4th circle. Right, next one is fourth one. Quarter circle or 1 by 4th circle. 1 by 4th circle theta will become 90 degrees, pi by 2 radius. Now consider this is y-axis and this is considered x-axis, right? Now between these two, 1 by 4th circle is okay covered. Now radius of the circle, 1 by 4th circle is R. it makes an angle theta value pi by 2 radians or 90 degrees. What is the induced magnetic field at the center of this 1 by 4 circle? Okay, magnetic field formula. What is the magnetic field? Mu naught I by 4 pi r into theta. What is the theta value here? Pi by 2. Mu naught I by 4 pi r into theta value is pi by 2. Pi by cancel here. So mu naught I by 8 r. We will remember this formula. Okay, due to the 1 by 4th circle, what is the magnetic field at the center? That is mu naught I by 8 r. Due to the circular coil, mu naught I by 2 r. Okay, due to the semicircular coil, mu naught I by 4 r. Suppose 3 by 4th circle, what is the magnetic field at the center? 3 by 4th circle. In case of 3 by 4th circle, another fifth application here, 3 by 4th circle, circular coil. Okay, theta will become 1 by 2 half plus 1 by 4 will become 3 pi by 2 theta value. One semicircle, one quarter circle. That is a 3 by 4th circle. Now this is one semicircular coil. This is 1 by 4th circle. Carrying a current I, the radius of this one is r. What is the magnetic field at the center of this 3 by 4th circle? So in this case, one angle made with 3 by 4th circle is 3 pi by 2. Okay. Now what is the magnetic field formula? Mu naught I by 4 pi r into theta. What is the theta value? Mu naught I by 4 pi r into theta value is 3 pi by 2. By solving here, we will get, okay, 5 pi cancel here. Now what is the magnetic field? 3 mu naught I by 8 r. Due to the 3 by 4th circle, 3 by 4th circle means one semicircle, one quarter circle, that will become 3 by 4th circle. It carries a current I. The radius of this 3 by 4th circle is r. What is the magnetic field induced at the center of this 3 by 4th circle? That will become 3 mu naught I by 8 r. Remember this formula. For complete circle, mu naught I by 2 r. Okay, for semicircle, mu naught I by 4 r. For quarter circle, what is the magnetic field? Mu naught I by 8 r. For 3 by 4th circle, what is the magnetic field at the center? 3 mu naught I by 8 r. So if we remember these formulas, we can solve the problems easily. Okay, so first one is right hand thumb rule. So what is the use of right hand thumb rule? To measure the direction of induced magnetic field. So the direction will guartinchukolamu. So next one is for linear case and circular case, what are the applications? How can we what are the formulas? For infinite coil, what is the magnetic field? Semi-infinite coil, what is the magnetic field? Circular coil, 3 by 4 circle, 1 by 4 circle, okay, semicircular. Okay, if you remember these formulas, we can solve the problems easily. Thank you.